So hello everyone. Till the previous video, I have discussed the CTQ one that I'll upload today, and rest of the CTQs most probably I'll provide today the videos. If it is not possible by today because it is under the work, then this means three videos of CTQ 2, 3, and 4 maybe. It may be three videos or four videos. It will be provided tomorrow maximum. So what I tried to provide yesterday was the complete discussion about the CTQ one, where I discussed aspects of gain calculation, DC biasing, and after that offset consideration, noise consideration, and all the things I tried to discuss in detail. In this video, I'll cover the CTQ2 and most related things that I can discuss about the circuit. I'll try to do here. So the motivation of this circuit is to get some differential output out of an input which is single-ended, or in say we have some structure, two structures are there. What I'll see about the circuit, there is a one input and two outputs, so it is nothing but single to differential ended that I already mentioned there. So for the noise consideration, first of all, you should understand that what is the noise and how it contributes to the output and how it can be referred to the input. So first thing is that what are the noise sources? So as I mentioned, or I clearly talked about this thing or noise in detail in a playlist called 5 transistor OTA. There you can see it. And in this, I'll give a little bit overview of this noise contribution due to this resistor and after that these amplifiers. And so I'll take one by one circuit, then we'll discuss then what is the noise contribution of each and every element including amplifiers and how it can be referred to the input so that we can compare two circuits, because input referred noise ultimately very important, also the input referred offset, so that we can compare any two circuits. Because at the output, if we can calculate the complete noise contribution or the offset at the output, but we cannot compare two circuits depending on the output noise and offset, because there is a gain factor which is introduced in this output noise or offset consideration. So anyway, we have to refer it to the input so that effect of that gain is not there, and we have only the input referred quantity so that the comparison can be held easily. So I will take one by one circuit. Before that, I will tell little about the resistor noise and the amplifier noise. So first the concept noise. So in the concept noise, if I'm just considering a noisy resistor, this is my noisy resistor that I call R. To represent it or the model it with the noise, what we can do, we can model it using some current source that I call IN, or this is the R. This is now noiseless. This is now noiseless, and this noise current source is nothing but I averaging out. It can be written as 4 kT by R, that is under root, or the mean square value of this noise current can be written as 4 kT by R. Also we call this noise voltage modeling. This is the current based modeling of noise, modeling of resistor noise with a current source which is in parallel with ideal resistor. Other modeling of the resistor can be like this. The star means there is a no direction specified for the noise, but yeah, if you want to give, then you can give any direction which is considered during the first iteration. It has to be constant throughout your means analysis. So if I call this is a noise voltage, and then this is my noiseless resistor. Now this is noiseless. So what is this Vn? Vn is nothing but 4 kT R is under root, and what is the mean square value for this noise voltage? That is a 4 kT R. There is also relation between these two. This I call modeling of resistor noise, with a voltage source. Okay, with a voltage source. So for relation that I can write here between these two, this IN mean square value of noise current can be written as mean square value of noise voltage across the resistor divided by this resistor square. That we can see here, that is a 4 kTr divided by this resistor square. It can be written as 4 kt by r, so that we can see the relation holds true. This is the 4 kt by r and this is the 4 ktr. So from this relation we can prove it or directly. And this is the mean square value. If true value we want to write, then we can write in terms of true value, it is nothing but simple voltage divided by resistor. That is a simple relation that we know, relation between noise current and voltages, okay. So this is the brief about the noise consideration of the resistor. Now I will consider the noise of the amplifier. So here the amplifier is a 5 transistor OTA inside it. So I'll directly model. If there is an amplifier given, you can simply model the input referred noise at the non-inverting terminal. This is called V noise of amplifier. And how it can go at the output, there are two ways. So this is the noise model, and whatever the circuit here, I don't care. But how it will go at the output, it will go at the output by like if this is my some other terminal, that is as of now 0 because I am considering noise only. So if this is the gain of this amplifier, how it can write the noise at output of this amplifier is nothing but this gain times noise at input, okay. So if I want to find this input referred noise at input, it can be simply write to calculate complete noise at output divided by gain if it is actual value. And if we have the mean square value of input referred noise, we want to calculate it, then mean square value of the output noise divided by gain square. And if anyway we have short circuit current at the output, the other way of modeling it is, okay, so this is grounded and the noise voltage considered on direction does not matter, but anyway I have mentioned, so no problem. If this I want to calculate noise, input referred noise, then if there is other way to calculate output short circuit current noise, okay, or I will say out. So how it can be written as GM of this amplifier, the net GM of the amplifier times this VN at input, or also the input referred noise with the output short circuit current noise at output divided by GM square. That is the mean square relationship. And actual relationship is nothing but input means voltage noise is what? Output noise current divided by GM. This GM is nothing but any stage general GM. If there is any block, that is a gain block, and it is has GM, then what we can see, this is a V1, V2, and this is my output current, I out. I out is what? GM times input differential, that is my GM V in minus V2, sorry, V1 minus V2. This is general relation. From this relation, this we call differential voltage, or we call whatever input voltage. This differential voltage can written what? I out divided by GM. The same relationship I tried to write for this noise consideration. But for the noise, the direction does not matter. First thing, for the noise, once the direction is decided, we have to stick on that throughout the analysis, then divide it, refer it on input. And if the output noise quantity, is a short circuit current, then divide it by GM to refer it to the input. So there are two methods to refer the complete noise at the input. That is called the input referred noise. Okay, that is called the input referred noise. So once the complete input referred noise information we have for the two circuits, we can compare. That is called input referred noise. So if there are two circuits, circuit 1, circuit 2, whatever their gain, I don't care about that. First I will calculate complete output noise, then I will refer it to the input by using their gain or GM parameters, depending on what we calculate at the output. If we are calculating total noise contribution as a voltage at the output, then we will divide it by the gain to refer it to the input, input referred voltage noise. And if we have calculated a short circuit current at the output, then we will divide it by the GM of this model or GM of the block, then we will refer it to the input referred noise voltage. Okay, so now I'll consider the circuit first, then we will calculate it, and then second circuit, and after that we will compare both noise specs. Okay, so first I'll consider circuit 1, that is the first circuit, circuit 1. What we have input here, this is the resistor R, 3R, R only. So when the noise of R is considered only, then what can be the circuit? For the noise analysis, we can short the input, and there are two ways where we can model the noise of this resistor R. One is our noise voltage method, other is noise current. So I'll consider here current, that you can understand why I'm considering the current. You will find easy when we'll consider the noise current here. Okay, so VOM. So when I will consider noise current, you'll see this is the direction, that is my IN due to the resistor R. So what is this? This VOP noise. VOP noise is what? This current times this 3R times this current, or I can also write it 3R of Vn of R divided by this resistor R. So it can be written as 3 VnR. Okay, so what is this? VOM noise due to this current is what? Minus 4R of IN of R. Okay, so what is the differential noise due to this resistor? V noise, or no, I should not write noise here. VN diff, VNR diff, I will say it as 7 VNR. Okay, so this is due to the resistor, only due to the resistor's noise. So in second case we will consider the only due to the 3R. So I will consider case 2, 4R only. So for the first circuit I will explain for the every source, and after that I will write for the second circuit directly. Okay, so for this circuit, what you see, again we will short the output, sorry, short the input, and the noise of 3R, we can consider the noise of 3R in also two ways. So one is the as a current source and one as the voltage source. I will consider here as a voltage source because we can handle it easily, because in series. So this is 4R. So for the 4R we will consider in series. Direction does not matter that much, still I am considering like this. So Vn of 3R. Okay, so what it can be written as, this node is 0, this node is also 0, so there is no current in this resistor, so there is no current in this resistor. So this can be written as what? Noise VOM noise due to 4R is 0. What we can write here? VON or VOP noise due to 4R oh sorry, 3R, that is 3R. Okay, we can write it due to the 4R also, but it is for 3R. So noise due to 3R is what we can directly write it as Vn of 3R, which is nothing but 3R, 3 times of resistor noise, 3 times of resistor noise. I am writing all the noises in terms of resistor watt because the resistor is 3R here. So what it can be written as, okay, so not directly like this. So VNR of for R it is like this. So the resistor is 3. So what it can be, 4 KTR. Now for the 4, in this case for the 4R, when only 4R is considered, okay, so due to the 4R we can also consider here with any of this direction I can write it as Vn of 4R. So due to this we say this node is ground, this node is also ground, so no current in this, 0 ampere, so no current in this, so this is 0. So VOP noise due to 4R is 0. And what about this? VOM noise due to 4R is directly Vn of 4R. Okay, so I am not writing this thing here, we will see this thing later. So this is what is the differential noise for the both. The differential noise for this is V noise due to 3R diff is what? Vn of 3R. What is here? Vn 4R differential, that is what? Minus Vn of 4R. So there is complete. So for the circuit 1, you can see here what is this? VNR diff for this resistor is 7 Vn of R. So what is total? So total resistor noise, total noise due to resistors for circuit 1 is what? Vn diff due to resistors. The total noise can be written as what? Is Vn due to resistor plus Vn due to 3R plus Vn due to 4R. So we know that we cannot add like this. So what we will see? So we will see there Vn of diff mean square is what? For the first resistor, that is 7 VNR square, or it is 7 square VNR square plus Vn of 3R square. So it cannot add like this, that I have just written, plus Vn of 4R square. So how we can write it here? 49 VNR square plus, if there is a, it is for 3R, so what it can be written is, if I put a R instead of R, I 3R, so 9 Vn of R square. For this 4 is R, 4R is there, so 4 Vn of R square. So I have written all the noises in terms of only the resistor noise. So what it can be? 16 and 15 and it is like 7. Okay, so is it 7 correctly? One thing I should see here. Due to this resistor only it is 3R. So it is what? It is 15 and 49, so 64. Okay, so the total noise is 64 VNR square. That I can write for 64 into 4 KT R, that can be written as 64 into 4, 256 KTR. There is a total noise contribution due to the resistor for the circuit 1. Now the noise contribution due to the amplifier for the circuit 1. we'll see here noise contribution due to amplifiers for circuit 1. Circuit 1 is continuous, so I am writing for the circuit 1, or it is not necessary also. So what is there inside this amplifier? This is the amplifier, this is a plus minus, that is nothing but a 5 transistor OTA that I already mentioned in the question. I'll talk about the detailed noise calculation of this circuit. You can see this thing in 5 transistor OTA playlist noise calculation, but directly I am writing here the input referred noise. So there are 4 noise sources, but okay, there are 4 noise sources. If I am considering only the input referred for this is my input pair, this is my out, and this is in. Okay, so what is the input referred noise due to this amplifier? So it is getting directly written, this is the device 1, device 2, device 3, device 4. Okay, so input referred noise for the amplifier, input referred noise is what? Due to any one transistor of this input pair, it is a 4 kT gamma GM of input pair devices, GM1 plus 4 kT gamma GM2. This is due to the input pair. So this is the output noise short circuit current. We'll refer to the input by just dividing the GM1, 2 square. That's the transconductance. That's the input referred noise. So what it can be, 4 kT gamma GM1 and GM2 are equal for general differential pair, GM1 equal to GM2. Okay, so this is nothing but 2 times divided by 2 times of GM1, 2 divided by GM1, 2 square. So the input referred noise which is coming out for this is 4 kT gamma by GM of input pair 1, 2 cross 2, which is nothing but 8 kT gamma by GM 1, 2. So this is the input referred noise due to this amplifier. Okay, and also these 3, 4 also contribute. So due to this 3, 4 transistors 3, 4, but I will not consider that because it is not that significant, but even it can be considered due to 3 and 4. It is nothing but output noise is 4 kT gamma GM3 plus GM4, and input referred is nothing but GM1, 2 square. So GM3 equal to GM4, so I can write it as a 4 kT gamma GM34, that is a short circuit current, divided by GM input pair square. So it can be written as 8 kT gamma GM1, 2 divided by GM or multiplied by GM34 divided by GM1, 2 factor. Okay, so this is due to the 3, 4 devices. So the complete and detailed analysis you can watch the playlist of the 5 transistor OTA, where I have covered this noise analysis concept in great detail. So with this analysis, I am not considering this term here. As of now, I am considering that this term is dominating, but you can consider both as well. So what is the contribution due to the amplifier? That I'll directly call amplifier noise 1. Okay, so if there is an amplifier, there are 2 amplifiers in the first circuit, so I'll consider it, this is an amp 1, so I'll consider A1. So if I consider the noise of this amplifier here, this is Vn of A1, then how it can be written? The effect of this transistor at output, effect of this amplifier's noise at output, VOP. So what we can see here, this noise is, this node is Vn of A1, this node is ground, so this is my 3R, R, 4R. So what is the noise here? So noise at output due to amp 1 is what? This noise is ground, this node is ground, so directly it can be written in terms of gain, that is 1 plus 3R by R, that is a 3. So 4 of V noise of amplifier 1, that I call is amplifier 1, that I call is amplifier 2. Okay, so what is here? Here we can see, okay, so here we can calculate like this noise voltage is here at this non-inverting terminal, so this is a non-inverting amplifier, so it can be written as VOM noise due to amplifier 1 can be written as minus of 4 VNA1. So this is a correlated noise. So differentially what will be VN due to amplifier diff can be written as 8 VN of A1. Similarly, when you consider the noise due to this amplifier 2 only, here I will consider for the amplifier 2 only, then we will short this input. So I am considering noise due to this amplifier 2. What the noise due to amplifier 2, that I have considered Vn of A2. Okay, so what it will be? This node is ground, this node is ground, and this node is nothing but a Vn of A2, and this is 4R, R, 3R. So what is this node? It is nothing but minus of 3 Vn of A2, and this has noise contribution of what? 5 Vn of A2. So differentially what it will have? So Vn A2, this is due to the A1. Differential is what? Minus 8 Vn of A2. So noise contribution due to amplifiers, noise contribution due to amplifiers kitna, that we can see here. Vn diff due to amp, ये कितना है? It is coming as, so if I add noise square terms like this, square value, it will be 64 Vn1 square, 64 Vn(a1) square plus 64 Vn(a2) square, and nearly both the amps have this similar noise, so I can consider it as a 128 of Vn of a square, where Vn of a square is nothing but that we can say it is the noise of that we have considered here in the 5 transistor pack. This is 8 kT gamma y GM12 plus 8 kT gamma y GM12 GM34 divided by GM of 12. So this is the noise at the transistors, at the input referred noise of the 5 transistor OTA, that is the amplifier's noise. So this total noise, total input referred noise for the circuit 1 is what? That is due to the resistors, Vn total, that I can write what is the resistor total noise? It is a 256 kTr, 256 kTr plus 128 Vn of AR square. This is the total noise. Okay, now I'll just go fast for the second circuit. Now the noise of second circuit, the circuit 2, R in series, noise of this resistor can also be VNR of series voltage source. So this way I will consider the noise of all these 4 resistors, and if I am directly going with the intuition that for the first transistor what is the noise at this point, if I am considering only this first resistor, and what is the noise at this point, it can be directly written as this input is shorted, then what it will be? It will be simply like the minus 3 of VR. So what is this? VOP noise due to this I call resistor 1, this I call resistor 1, resistor 2, resistor 3, resistor 4. I am directly writing it. So V1 of 1 is what? It is directly minus 3 Vn of R. Okay. So what is the VOM of noise 1? 1 means resistor 1 is what? This is nothing but plus 3 Vn of R. Vn of R. Okay. So due to this 3R resistor, what it will be? Due to 3R resistor, this is ground. So VOP is what? This is due to R. Due to R1. Now VOP of N2, that I will means 3R. So what it will be? It will be directly, okay, so this is 0 current, so OP is 0 due to this 0. So what is VOM of N2? It is nothing but what it will be here. So this okay, so due to this resistor, what it will be? This is a noise. Okay, not wait, not it is a not 0. It is our directly Vn of 3R. So what it will be? Minus Vn of 3R. So due to this 3R resistor, that we call 2, which is nothing but 3R resistor. This is due to resistor R. So now third case due to R3 means that is your R only. So what it will be? Now I consider series source. Due to this ground is shorted, no current in this branch, no current in 3R, so VOP will be 0. So VOP noise due to third resistor, that is R, is 0. V noise due to this third resistor, it is directly, it can be written as minus Vn of R. So now fourth case, VOP of 4 due to the fourth resistor, that is 0, and VOM due to 4 resistor means that is a R, equal to directly Vn of R. Okay, so total differentially we can calculate differentially what it will be, 6 to VNR. Okay, so total resistor noise, output is what? Vn diff due to resistor. Total is what? This is a minus 6 VNR. That if I will write in a square, then it will be whole square plus that is 2 means 2 Vn of 3R whole square. So this is also square plus this is VNR square plus VNR square. Okay, so it can be written as 36 VNR square plus 3R means 4 into that is a 9. 36 VNR square plus 2 VNR square. So it will be 72 74 VNR square. It can be written as 74 4 KTR. So it will be, it is what amount? That amount is going, I think you need to calculate this, check the calculation once. I think it is correct. 36. So 36, that is a 4, so VNR square. Okay, 36 9 3. Okay, no, it is not 3. So 4 KTR. So what is the VNR? Just I would write this. What is my VNR 1 R square is what? 4 KTR. So what is the Vn of 3R square? It will be 4 KT into 3R. That is my 4 KT to 3R means 12 KTR. Okay, so I think this is something written incorrectly here. So it will be not 9. It will be, this is corrected here. So it will be 4 into 3 12 VNR1 square. So this is fine now. So what is total? Total is, So what is total? 12, 30, 48, 48, 50. 50 VNR square. Okay, 12, 36, 48, 50. 50 VNR square, 50 volt. This is 200 KTR. So this calculation is also, I think, missed here. So here it is what VNR1 square into this is 3 only, this is 4 only. So what it will be 64, 39 on 756. So it will be 56. Sorry, 49 and 756. 56. So accordingly it will be like 228. It will be 228 KTR. Okay. So it has to be corrected. It has to be corrected. That I will write here 9. Okay. So this is like that. This was a mistake that I have corrected here. Now you can see here for this. So now total noise contribution due to the resistor is done. So noise contribution due to amplifiers. Noise due to amplifiers. So we have to see the circuit again. So if I am considering noise of this is my Vn of amp 1. So what it is this is my R, that is 3R. It is going to VOP R. So this is VO. Okay. So what is the noise due to the when noise of only first amplifier is considered, then what the expression we can write? So it is nothing but this is coming as VOP noise due to amp 1 is coming what is directly 4 of Vn of A1. What is this? Noise OM, and due to amplifier 1 it is coming as minus of 4 Vn A1. Okay. So what is this? So this is directly 8. Okay. So differential is what? Differential here 8 Vn of A1, that is differential noise. So for the noise source of this transistor only, I am just telling here, if this is the only noise source for this, not here. Okay, better to consider here. In this terminal. Okay, I write here. Better to consider in this other terminal. I will draw again fast. This is 0 now. This is 3R. Okay. So if I am considering noise of amplifier 2 at its non-inverting terminal, then what is the result? So result is that, what is this? So this is grounded, no current is here, also no current in this branch, 0 amp. So what is this output? This output is 0. This is VNOP due to amp 2 is your 0. So if this is 0, then what it can be? It can be Vn due to OM A2. It is nothing but means 2 Vn of A2. Okay. So what is total due to noise? Total noise due to amplifiers. For circuit 2, which is nothing but what is here? That is a 8 Vn1. Vn diff total due to amps is what? 64 V of A2 square. Nearly I am considering they are same. So 66 VNA square. So this is the total differential noise due to the amplifier. So now net noise, total noise is what? This 200 KTR plus 66 of VNA square. Both the amplifiers are similar. So if I consider both the circuits, then what is for this circuit? It was not 256, it was 228. Okay. So now conclusion for circuit 1 for okay. So for the first circuit, total noise is 228 KTR plus 128 plus 128 Vn of A square due to the amplifiers. What is here? Total noise is here 200 kTr 200 kTr plus 66 VNA square. So if I compare both the circuits, we can see, if the calculation is correct, then noise in this circuit 2 is less than this noise at the output, and differential gain is same. Differential gain is what? Gain for the first circuit is what? Gain for this first circuit is 4R and minus 4R, 8. So okay, gain is 8 here. So what is the gain here? It is 4. That is minus 4. Yeah, gain 8. So for both the circuits, gain is, differential gain is 8. Gain is same. So accordingly, we can find the input referred noise. So we will see directly that in this circuit the noise is more than this circuit. So we will select the second circuit for a single differential ended circuit, means signal conversion, if we have these two circuits in option. Then what we can do here, that we are seeing that it has a 66 VNA square. And what is the VNA here? VNA is coming what? Simply it is coming as VNA square, that is nothing but 8 kT gamma Y GM1 2 input pair 1 plus GM34 divided by GM12. So it has less noise than this, so nearly 2 times. If this noise is increased, then we can say that still we are better than this, because we have 200 kTr here and 220 kTr here. So if we have to optimize the second circuit power, then we can optimize, because if we are going double of the noise due to the amplifier's contribution, and what can we see here, the amplifier's noise can be doubled, even we are better than this circuit. So doubling of the noise simply means this GM12 nearly can be halved. And also from here we can see that what are the parameters that can be adjusted. Nearly half of this means we can reduce our current by 4 times. Reduce current by 4 times. So if we can reduce the current by 4 times, then we have good power relaxation in this second circuit case, because we have better noise specs for the circuits. So we can reduce the current burning in that circuit, or in amplifiers especially. Whatever the quiescent current that we are setting for the amplifiers can be reduced much, because we have 66 factor here only and 128 factor here. So this is the good thing in the second circuit. So I think based on this, you can see that what is your calculation, and if there is any calculation mistake, you can recalculate it. But the concept is this only: first we have to calculate the individual noise analysis for the resistors, then after that for this amplifiers, and overall we have to compare the circuits basis on that. And I think I tried to cover many concepts here about the noise calculation, how to calculate exactly. So if there is any doubt, then you can post in this, and this is, I think, enough for this circuit analysis of the CTQ2. Okay, so I will recap once. So what we have done, this CTQ problem we have stated here. After that, noise concept I have explained, how to model the noise of the resistor and how to model the noise of the amplifier, and then what are the points that I mentioned, the important points are there. And after the circuit 1 analysis, due to the resistor noise, and after that due to this amplifier noise concept here, and after that we have calculated the noise contribution due to the amplifiers only. And then for the second circuit, again for the resistor contribution, the noise due to the resistors, and after noise due to the amplifiers, then the overall noise at the output, and we have the equal differential gain, that is a 8. So we can refer this noise to the input, and then we can compare, and according to that we can have the power relaxation for the second circuit. So it is enough for the circuit. Thank you.